Last class we were talking about how to control the speed of a separately excited motor with the 4 quadrant operation. So, if you see here, this is the torque speed characteristics. Okay. We will control the voltage, armature voltage V, such that the current will quickly come to 0 from A to B. A to B is as far as the speed is concerned, it is a same speed, parallel line with respect to TL with the x axis. So, speed cannot change instantaneously because the back EMF cannot change instantaneously because of the mechanical time constant. Okay. Mechanical time constant will be always greater than, we can assume here greater than the electrical time constant. So, A to B, the current will come to 0 immediately, and still we are controlling the voltage. So, slight reduction in the voltage at this point, the torque is 0, that means our back EMF plus the back EMF will be equal to the our applied voltage. So, current will be 0. A further reduction in the voltage, current will start flowing from the motor, that means from the back from due to back EMF, it will flow from the motor to the our converter side. So, the equation will be like this, previously it was minus, it will be plus. So, here that means instead of drooping here, here it will slowly increase, slope is this way, same slope. So, here from B to C, current is negative. So, the torque is also negative. So, quickly it will come to C. This TL maximum, that is this point is has to be limited by your controller, this point. That means your applied voltage, through applied voltage you have to control, so that always maximum torque is applied, negative torque is applied to the motor, or maximum current is taken from the machine such that machine will decelerate. So, A to B is current is 0, that means machine is from B to C, current will start in the opposite direction. Okay. Then from here onwards maximum negative torque is applied, and C to D is the deceleration, that means we want a speed from B to D. So, D is the point, the horizontal point where we want the speed here, that is we want the operation from A to F. So, the moment it come to the correct speed, that is back our motor come to the correct speed, we will adjust the voltage such that slowly we increase the applied voltage, so that the negative torque, the current will slowly reduce. So, it will go along to the many parallel lines in a horizontal way here, it comes to 0 here. So, these are depend on the electrical time constant, but C to D is a slow process that depends on the mechanical time constant, machine is slowly decelerating. So, it will go, it will come to here, again we apply voltage such that motor should not slow down, we have to apply a positive torque. So, motor will slowly come to this position. Okay. So, this is how we have to do the thing, but in with respect to time, a typical torque speed carrier is how it looks. Okay. Let us take, this is our speed N, I will take it like this, speed, this is the x axis for the speed. Okay. Now, machine is running with a constant speed, that means according to our previous case, the machine is running here, machine is running at A. Now, we want to come to F. So, machine is running here. Now, we are asking the machine to go to a, instead of speed speed reduction, to go to a negative speed. So, from here ideally it should go quickly as good as, but this is not possible, this is a step change. So, the next response is a first order lag with mechanical time constant, it should slowly go and come to the required speed like this and stay there. Okay. You should not have transient like this, smoothly go, our controller should take care there. Then what will happen to the, this is our final speed. So, what will happen to the current here, let us take the current axis here, armature current. So, previously for this speed and the torque, the armature current was like this. Let us assume this is our IA. So, maybe for clarity we will do with a different color we will give. So, this is our IA. Okay. Now, the moment we give a speed command, change command, we want to give a negative torque. So, quickly compared to this mechanical, now quickly this will come to the maximum IA maximum, rated maximum current here quickly. But if you expand this one, this will also with a first order lag it will go depending on the electrical time constant. But with respect to the mechanical time constant, this is fast and it will come there and current will stay there till it machine reaches that speed. When machine reaches that speed, let us see, we are controlling the armature voltage. So, armature voltage, let armature voltage and back EMF, let be this is the axis. Let us say this is till this point, let us say this is the armature voltage VA. Okay. Now, where is the back EMF? Back EMF will be somewhere here. We can use a different color. Back EMF will be somewhere here. This difference is equal to our IA RA. This is equal to IA maximum rated value. So, this is our EB. This is our EB. Now, the moment it changes, what happens? VA will immediately change here. That means, VA will change immediately change and come here such that VA will come here such that now this EB, this difference will be equal to mu IA maximum into RA. Now, here onwards, back EMF cannot change instantaneously, speed cannot change instantaneously. Here onwards, till this speed is reached, we are applying the varying the armature voltage. So, that armature voltage from here onwards slowly come here. So, as the speed decreases, what will happen? You always maintain the IA maximum. So, this from back EMF will also slowly decrease with respect to speed. So, back EMF will vary like this, such that throughout this variation, as the speed varies, we will control this armature voltage so that this drop IA maximum, that depends on the maximum load current, rated motor current, IA is always like this. The moment comes here, speed was reached. Now, we want the previous IA only required to drive the, if it is a load is the same. So, here VA will quickly come down to this point and stay there. So, that now the new this is equal to our old IA and RA. So, this will slowly reduce from here and come here. So, if we expand these points, this one and this point and this one, this all with respect happens with respect to electrical time constant. That is electrical time constant LA by armature inductance divided by RA, electrical time constant. And this speed change from here to here, that is due to the mechanical time constant. Okay. So, all the electromechanical time constant, we will come to that one. So, what we want here, the control, all this smooth transition is possible because we are controlling this armature voltage such that always maximum current is, negative current is taken from the machine as the speed varies. And once it comes to the required speed, quickly we come to the required driving current for the driving torque. Okay. So, if you do not properly control, what will happen? The machine can go like this and large oscillations and can settle in after some time. So, here also if the control is not proper, this current can go like this, oscillations can happen. So, here also that reflect here also it can get into oscillation. So, instead of settling here, it may, if the controller design is not proper, it will take long time. So, we have to design the controller like that. So, how to design the controller? So, we will like our AC to DC controller, we will form a closed control block, and from the block we will have the speed control and other control, like in the AC to DC, if you require inner current control, we will also have an inner current control here, then we will choose the controller. So, before coming to that one, AC to DC converter, that is 4 quadrant operation is possible. Now, let us take, if you use phase control converter for high power applications, we are using, how we will control the 4 quadrant operation with the DC motor. Very quickly go through that one, and then how you make the firing sequence, firing control for a phase control converter. Sine triangle PW, it is easy to generate sine triangle, and phase control how we generate. Then we will come to the closed loop controller design of the DC. Let us talk about the phase control converter, how we can have 4 quadrant operation. Let us take the converter like this. This is our phase control converter, 3 phase like this. Okay. This is our mains, our ABC or ROB system coming here, 3 phase mains. Okay. Now, our motor is here connected. Now, if you see here, previously we said we want to take back energy from the motor. So, current has to reverse, but if you see here, current can only go in one direction because of the thyristor. So, we should have another converter, we should be able to take current in the opposite direction. Suppose the back for this rotation, suppose the back EMF is here, if you want to reduce the speed in the same direction rotation, we have to take current. Previously current was going like this, now current we should take it the other way. So, we require another converter connected in a anti-parallel way. This is called dual converter. Okay. Now, suppose if we have a switch like this, which can be opened and closed like this. Now, for the machine to run in this direction, if we want a positive voltage like this, we will close this one and we will give the correct firing angle alpha 1 here. So, the machine is running with a particular voltage. Now, if you want to reduce the speed, what we can do? We can slowly reduce the firing angle by this voltage appearing here, that is E0 alpha 1, that is this one coming from here. We can reduce so that the current, this one will slowly come to 0. We can sense this current. Once the current is 0, we can close this one and we can open this one. See, this can be opened and this we can close it. So, what happens? Now, current is 0, machine will slowly send current in this direction. Okay. So, we can control this firing angle such that now this voltage is controlled. So, this inverter is working in the inversion mode. So, for both the converter it is firing angle is equal to cos alpha. So, for one converter it will be working like this. For our converter, so this is our E0 alpha. Other converter it should be the other way, this way. So, for this converter, this is the rectification mode, this is the inversion mode. So, power is that is voltage is negative. For this converter alpha, if that is rectifying mode, then positive will come here, negative will come here. Now, we want the positive here, so it has to go to the inversion mode here. So, firing angle has to, for this one, alpha 2 should be greater than 90 degrees. So, it will be in this direction. So, we will come to that one now. So, we can take back the energy here, and once the speed has come to the correct speed, we can slowly increase this one in the rectification mode. Slowly we can increase so that the current from the motor can be made 0, and the moment 0 quickly we can open this one, again we can close this one. So, that way we can control. See, but here the problem is there is a this is a slow process, because there are switches we have to sense and on and close. Okay. For fast control, automatically the system should, or controller should be able to sense, and the system should be able to, without this mechanical switch, it should be able to send power back to the mains as well as receive it also. So, 4 quadrant operation. Instead of that one, what is done, these switches are removed. So, we will let us remove the switches now. Okay. These switches, this portion we will remove. Now, we will connect a reactance here, and at the center this is connected. Okay. So, for this converter this is alpha 1, for this converter this is E0 alpha 2, okay, and this is our speed omega, okay, and this is our E0. E0 is here. Why this? See, by appropriately choosing the firing angle here, E01 and E0 alpha 2 we can make it same. That means same voltage like this. For firing angle for this one, if it is this one, for this it is here alpha. Okay, this is alpha 2, this is alpha 1, such that both converter will be having the same voltage. But because of this polarity, if the motoring mode, current will go only from here to here. Okay. Now, why this inductance is, this is dual converter in circulating current mode. See, we are talking about the E01 and E02. The DC may be same, the instantaneous ripple may not be the same. Let us take a typical example, ABC waveform here. This is our A, so ABC waveform. So, for the alpha 1 it has to be start from here, alpha 1. Alpha 2 it has to start from here, because this converter. Now, for alpha 1 and alpha 2 for same voltage if you take, so for a particular firing angle of alpha 1 is equal to 60 degree if you take, then the waveform will be approximately the ripple waveform, you can draw it, will be, it will be like this. From here, sorry, it will be like this. This is 60-degree duration. You can draw it. This is not matching. So, for the converter 1, that is, this is converter 1. This is converter 2. So, with the same firing angle alpha 2, the DC voltage is the same. So, but if you see here for the converter, other converter, it will be in this case, in this way it will happen. So, if you see here, the average for this one and the average for this one are the same, but the instantaneous ripple are not the same. So, instantaneous difference in the ripple has to be dropped. That is why we are put this inductance, okay, such that we will draw this waveform slowly, such that the difference in the voltage should be dropped across the inductance, okay. So, let us take this voltage is equal to ER, ripple voltage, I will take it ER. So, this is stopped at the center point, so this is ER by 2. So, voltage across the load is 0, with respect to time, instantaneous time, including the ripple voltage is equal to, this is our E alpha 1, not 0, I am E alpha 1 with respect to, that is the ripple voltage, that is this one, E alpha 1 t minus E r t divided by 2, okay. Now, we know E r is equal to, because of the center tap, E r is equal to E a 1 E alpha 1 t minus E alpha 2 t. This includes the DC as well as the ripple part, okay. So, DC will cancel, only the ripple will come across this one, because both has the same DC. So, inductor will only support the ripple value. So, if you see here, E0 is equal to, E0 t is equal to E alpha 1 t minus E r by 2. So, that means minus of E alpha 1 t divided by 2 minus E alpha 2 E alpha 2 divided by t, okay. So, this will come to E alpha 1 plus E alpha 2 by t. This is the ripple voltage coming across, including the coming across E0, okay. Now, for a typical firing angle of alpha is equal to 60, how the waveform will, I will try to draw that one. So, this is our E1 or VABC. Okay. Now, VB 120 degree phase shifted. EB, then this is our EC. Okay. Now, alpha 1 is starting from here. So, alpha 1 is 60 degree. So, alpha 1 is equal to 60 degree means it will be here. What should be the alpha 2? So, we are firing the converter 1 and converter 2 such that for the converter 1 the output voltage is equal to E max E 0 maximum, okay, E maximum into cos alpha 1 should be equal to E maximum to cos alpha 2. Okay. That means cos alpha 1 plus cos alpha 2 is equal to 0. That means cos alpha 1, because other converter is in the inversion mode. So, it is more than 90 degree. Cos alpha 1 is equal to minus cos alpha 2 is equal to cos of 180 minus cos 180 minus alpha 2. So, this shows that alpha 1 plus alpha should be equal to 180 degree. So, to get the correct DC voltage for the two converters, if alpha 1 is fixed, alpha 2 will be 180 minus alpha 1. If we can take care of this one, for alpha 1 is equal to 60 degree, alpha 2 will be 120 degree, then the DC voltage will be the same. So, let us draw that waveform now. Okay. So, this is the alpha, alpha is equal to, alpha 1 is equal to 60 degree. So, alpha 2 should be 180 degree. So, if you see alpha 2, it will be from here. 180 degree means it will be somewhere here. So, this is alpha 2, it starts from here. Alpha 1 is 60 degree, alpha 2 starts from here, that will be 180 degree. So, if you draw the waveforms, ripple voltage waveform, we can draw it like this. For the converter 1, it will be, this is the axis, see, you can see the 60 degree duration ripple for alpha 1 is equal to 60 degree. What will be for alpha 2? Alpha 2, if you take with the 120 degree, it will be like this. Okay. Now, A is equal to, output voltage will be, this one, this is E alpha 1, this is E alpha 2. So, E 0 t is equal to E alpha 1 plus E alpha 2 divided by 2. So, if you do that one, this will be approximately, ripple voltage will be something like this, it will happen. Okay, this way it will go with respect to a DC value. So, this you can draw it. See here, if you see here the DC, there is a ripple here. This ripple will be ripple current, and this ripple voltage will be controlled by the armature inductance of the machine. Now, what is our ripple voltage for this question? Ripple voltage that is coming across our circulating that inductance to suppress the circulating current, that is ER. ER is equal to E alpha 1 minus E alpha 2. If you see here, it will be something like this. Here the average value will be 0, okay, to show that one. Okay. So, average voltage drop will be, so this ripple voltage will be dropped across the converter. Now, see, so far to complete the phase control converter, all this firing angle all depends on the our reference sinusoidal voltage. So, with the reference sinusoidal voltage, how do you generate the firing angle? A typical example. It's many books it's available, but we will just for sake of continuity and completeness, we will try to give some schemes, discuss about that one. Let us take a, instead of 3-phase, let us take a single phase converter. 3-phase can be derived from this one. So, firing circuit, firing angle control circuit. Here, this is our, let us draw our converter here. This is our mains single phase. This is S1, S2, S3, S4. Now, how do you control the circuit? Let us, all the firing angle is with reference to our main circuit. Mains is 230 volts. So, to control level we have to step down that one. So, we will have a step down transformer, maybe 230 to 10, 230 into root 2, that is 230 is RMS into root 2 is to 10. So, you can have control level of plus or minus 10 level. Okay. So, you have a transformer like this. We will use a center trap transformer. So, V1 and V2. This we give to a zero crossing detector. Zero crossing detector. Zero crossing detector. Using operation amplifier you can use it. Okay. So, zero crossing detector, the output will be a what? It will be a, you can make zero crossing detector 0 to positive. So, when it is positive, it can be it can be like this, zero crossing positive like that. This you give to a ramp circuit, ramp generation. To the ramp generation, we will give it to a comparator circuit and low comparator. Using operation amplifier or 3-1 comparator, you can give it. Here we give the control voltage EC, this variable. So, this from the converter output we can give to a mono short and we can generate the required pulse, gate pulse duration for the thyristor. So, how it will look? You have the sinusoidal reference. After stepping down, it is negative also. So, this positive side is for generating pulse for S1 and S3, negative and the negative, the opposite waveform, this one, this is for S2 and S4. So, this we can get. So, V1 is positive with respect to the center tapped, this is V1, this is V2. So, this is our V1 and this is our V2. Okay, this we are giving to our, we will talk about the firing pulse generation for S1 and S3 for the positive half cycle. Same thing can be used for the negative half cycle also. So, zero crossing detector. So, zero crossing detector, it will be Okay. Now, we have a ramp circuit during the positive side. So, ramp firing will be positive side. This same ramp circuit we can use it for the negative also. Okay. How do you generate firing angle? And this is compared with EC, our control voltage for firing angle variation. So, this is our EC signal. This we can vary. So, when this comparison point, the monoshot output will give the required pulse here for S1 and S3, and this is for S2 and S4. So, this is for S1, S3 pulses, and this is for S2 and S4. This is for S1 and this is for S3. Okay. So, by controlling the firing EC, we can have firing angle at 0 or 180 degree. Now, how do you generate this ramp? It is very easy. So, you give it to an operation amplifier circuit. I will draw this one here. See, let us take a using operation amplifier. Many ramp generation circuits are available in the book. So, you have this one. There is some 22K you can put it, and a 10K port you can make it minus 15 volt. So, give it here, and there is a capacitor here. You can choose your capacitor, so that RC time constant we can adjust, so that this capacitor will slowly charge. Then this charging portion charge at this point, when 0 crossing, we should discharge it. So, for that purpose, this 0 crossing points you have to detect again through a monoshot at these points, even here also, small pulse. This pulse at this point, we should capacitor should discharge quickly. So, for that one, we will connect a transistor here. Maybe we can put a small resistance also here and give the pulses here, these pulses you can give it here. So, whenever the 0 comes, it will quickly discharge. Output is always positive, negative, it goes like this. So, ramp we can generate. This is a typical circuit. This is this point here. This comes here, is across here. So, whenever the pulse is there, it will quickly discharge, and when the pulse is not there, it will charge. That is, pulse is not there, that is, these pulses are not there, this is the point. And by varying the EC, we can have the firing angle control from 0 to 90. So, in this circuit, if you see for phase control converter, we know it is E0 alpha is equal to proportional to not alpha, it is cos alpha. For 3 phase, it is, we know it is E0 alpha, the output is equal to E maximum into cos alpha. Now, see, this is for the single phase. Suppose if you want to make it for 3 phase, what you have to do? See, S1, S2 and S3 are switched 180 degree phase shifted with respect to S1 and S4. Now, in our 3 phase circuit, this A phase and B phase, C phase are 120 degree phase shifted. So, instead of generating this 180 degree, you generate 120 degree pulses, phases by step down the mains. Then, for the each step down voltage, you generate this pulse from the individual, based on the individual phases, generate this pulse and give to the top and bottom. And for the next one here, B phase, from the B phase top and bottom you generate, and C phase you can generate it 120 degree also possible. But if you see here, output is proportional to not alpha. We are varying the output based on this EC is proportional to we are varying EC from 0 to alpha here 180 degree. So, the firing angle, that is the alpha here, from here to here to here, alpha is varied from 0 to 180 degree with EC vary, but output is varying proportional to cos alpha. This is not a linear control. For linear control, input EC varies, output also should vary proportional to EC. So, how we can do it? This is called ramp comparison technique. For simple power supply generation we can use it. For motor drive applications we should have linear control. So, there we should use cosine comparison. See, we want EC to vary not proportional to alpha, EC to vary our control voltage, EC to vary proportional to cos alpha. Let us take our control voltage EC is proportional to cos alpha, that is some E maximum into a control voltage E maximum into cos alpha. Now, what is alpha? Cos alpha is equal to, now from this one alpha is equal to cos inverse EC by E maximum. Okay. Now, our output voltage E0 alpha is equal to E0 E max, the maximum for alpha, firing angle alpha is 0 into cos alpha for a 3-phase fully controlled converter. This we substitute this one. If you are varying EC, EC is proportional to cos alpha. That means our control voltage EC, control voltage is proportional to cos alpha. Okay. So, here it will be E max into alpha we are substituting cos of cos inverse EC by E max. Okay. This is the control voltage maximum. This will be equal to E maximum divided by the control voltage maximum, maybe plus or minus 10 volt into EC. So, here if you see, if you vary the EC proportional to alpha, our output voltage will be, this is constant, will be proportional to EC. That means this is equal to, this is always constant, output maximum. So, this will be equal to some constant K2 into EC. So, output will be proportional to EC. This is called cosine control. So, let us say how it can be done. Again we will take the, for single phase only we will take, 3-phase corresponding reference sine wave 120 degree we have to generate from the mains. Now, let us take a single phase control. I am representing switches like this. This is 1, 3 and 2, 4. Okay. This is our waveform. Now, let us draw the waveforms. This is our reference waveform from step down waveform from the mains. Okay. This is the negative part. Okay. Now, we want EC to proportional to the cos alpha. So, what we do, the same EC, here we will integrate the main this waveform and make it a cosine, we will generate a cosine waveform here. If you see here, the cosine waveform will be like this. This way it goes. Okay. Now, we will generate an EC positive as well as negative. This is EC positive. Let us take EC positive. as well as EC negative minus EC. Now we will generate the cross comparison using comparators, will generate various signals like this. Okay. So, let us take the positive side. Here, then again here it will be 0, then again it will go high here. Okay. Negative side using comparators, here we generate signal like this. Again it will go like this. That means that is whenever we are comparing EC with our this waveform, cosine waveform, then all these points, positive going points, that is, he will generate a pulse. Okay, and here also. Here positive going here, next one. Okay, this one will give it to T1 and T3. This one will give to T2 and T4. Okay, so firing angle is proportional to cos alpha. When firing angle is equal to 0, firing angle is here, it will come. So, with respect to mains at 90 degree we are finding. So, cos 90 is equal to 0, output will be 0. When the firing angle EC is maximum, we are firing at alpha is equal to 0, you will get maximum output. So, we get maximum positive and voltage control for positive as well as negative, which is not proportional to cos alpha, it is proportional to alpha. So, that means proportional to EC. That means when EC is maximum, output is maximum. EC is maximum here means automatically firing angle is 0. So, output will get maximum, and variation of EC is proportional to cos alpha. So, it is comparing with the cos alpha waveform. So, this way we can have output voltage waveform. Okay. So, many textbook use circuits how to generate for cosine comparison. Cosine comparison. Cosine comparison, that is, control voltage is compared with a cosine wave. Cosine wave derived from our step down mains waveform. So, this is for one phase. For the 3-phase system, the next 2 and 3 will be at B phase. So, you generate another sine wave which is 120 degree phase shifted and generate its own cosine waveform, and the next one 240 generate cosine waveform and fire it like that, and generate only these pulses T1, T3. Okay. So, this way you can have a voltage control, cosine comparison for voltage control. Now, so far we have studied about control rectification, AC to DC converter using phase control converters, its problem, what is output voltage, how do you control the firing angle, and what way the output varies with firing angle, and how we can generate the firing pulses. Also, how we can have a converter with a 4-quadrant operation, that is a dual converter, and then circulating current to take care of the ripple voltage level, we have talked about it. Then for we also studied about front end converter has the power factor problem. Then we have studied about how we can control the front end the phase control converter as semi converters. We have studied this portion also. Then we have talked about 4-quadrant chopper. Okay, 4-quadrant chopper is a single phase inverter circuit where we can have 4-quadrant operation and proper PWM controller, we can have a unity power factor. So, various converter controls we have studied. Now, we have introduced last class how a speed control of the DC motor we should do, such that we should have a smooth speed change, and we have to accelerate and decelerate the machine as quickly as possible within the permissible time constant of the system without much transient, how we can do it, and how the response should look like, what we talked in the beginning of today's class. The next class we will do the closed loop control. We will draw the closed loop block diagram for the separately excited DC motor control, and how we choose the controller parameters, same like in AC to DC converter, such that the motor will respond, will have the optimum response without much transients. Okay, this we will study in the next class.